Hello, so today I want to talk about cosine and sine, the trigonometric functions. Sine and cosine, whoa. And these are super important in general, super important in math. If you're interested in doing anything technical at all, and they're definitely important in games and I'd say in programming in general. But if you hate math, you could maybe get away with avoiding them for the most part, but they're super important. And I will explain in more depth, but the way it's generally described is as these ratios of right triangles. I can't draw. So ratios of the sides of these triangles, but I'm going to explain it from a different angle. Get it? And I have to learn how to draw a circle, or else we're gonna have a lot of trouble here. So a circle, how do we define a circle? You could have an equation for it, but more basically we say that you have a fixed length, right? You pick a point and then you, let's say, take a string with a pencil at the end and then trace out a circle, and the point is that everywhere on the circle has that same length away from this point. Okay, so it's everywhere on the circle is a fixed length away from the center. And the way we're drawing this is just that the center is the point 0, 0. We have an x-axis and a y-axis. And so for me, if you pick some random place on the circle, but let's pick somewhere over here. So something like this. We draw a line there. So this is a radius of the circle. And you can always look at this and just say, well, you can choose your units. So this could be 1 meter, 1 kilometer, it doesn't matter what it is. If it's, you measure it out and it's 5.4 feet, you can decide that in your little personal world, 5.4 feet is the unit 1. See what I'm saying? No matter what the length is here, we can always just define this as being the number 1. And if we do so, then the cosine and sine are these shadows that fall onto the x-axis and the y-axis. So so these sort of perpendicular shadows, like if a light is shining straight from up above down onto the x-axis, then this length here between the origin, between the point 0, 0 and here where the shadow hits, this is cosine of the angle. So this angle, let's just call it alpha here today. I'm in an alpha mood. Cosine alpha is this shadow right here. Another way of saying it is that it's the projection. Now usually, so I'm going to go from here and then talk about the ratios of the lengths of the triangle. Usually the discussion goes in the opposite direction. But I think this is sort of more fundamental and more really what it's all about. It's about, so I think that that projections are more general, and sine and cosine sort of give us our first foothold into the world of projections. So you can imagine that if you're interested in geometry and you want to do a lot of math, then these shadows are of interest. So if I draw it this way, which normally you don't draw it like this, but I'm just saying there's this shadow going this way that we might be interested in. And that along here, that would be the sine of alpha, this y coordinate. So basically, and actually I'm gonna I don't want this arrow here, or this line actually. I was just demonstrating that. This point here, I'll draw like this distance here. This shadow, the shadow's going horizontally, but it's this vertical part here. is sine of alpha. So cosine and sine as functions can be very confusing, and especially if you're trying to start, again, starting from this whole ratio of the sides of a triangle story. It can be very confusing, but if you just boil it down to these projections, these shadows, it's kind of somewhat straightforward. So anywhere we pick on this, let's do blue, I guess. Anywhere we pick on this triangle, or sorry, on the circle, and we call this the unit circle because we have chosen a radius of length 1. We sort of drop this, we draw it this way. So not, some people get a little confused and they pick like, let's say we pick here. No, let's say on this side. Say we pick here. They might choose to draw things another way, like this way. That's wrong. This is not the way you draw it. You can talk about these angles and things that will happen. In general, actually, this is not completely uninteresting, of course, as most things in geometry are. If you do this kind of thing, actually, this angle here, so if this is alpha here, and then this from here going out to the same points, and if you call this angle beta, then actually beta here is twice of alpha. So actually this is interesting, and in trigonometry, this whole business is, we're talking about trigonometry. Notice that it has the word, the TRI from triangle, same root. At some point you might talk about half angle formulas and double angle formulas, like you want some, for example, there's a bunch of identities. So cosine 2 alpha is going to be, so let me choose theta, just so that we're not looking specifically at these other graphs. It just so happens that this will be equal to cosine squared theta minus sine squared. This is one of the identities. Whoa. I have it sort of memorized here. Minus, why does it do that? Sine squared. Okay. And the picture, whenever somebody starts talking about half angle or double angle formula stuff, I always kind of look at this. I'm thinking about this kind of setup. Not that that's always going to be helpful, but that's my default go-to, and they do come up. But yeah, so that is interesting. However, that's not how we normally draw things. Normally, we have the circle, and we draw it going out from the origin to the point. So if this is your point over here, out from the origin to the point, and then always we drop down to the x-axis. That's sort of just tradition, because we're starting with theta equals 0 is over here. So if there's no angle, we imagine that there's this vector here. I'll do orange now. Can I make it thicker maybe? We imagine that there's this big vector here. Well, I do anyway. And so if it's perfectly on the thing here, so again, it's always 1. It's like a clock, and the length of this hand is always the same. And at least for our purposes right now. So when it's here, we say that the angle that we're talking about is 0, because it's always like between this position and somewhere else. So if the clock hand is going here, now our angle is here. Okay, this little part right here. How do I redo? What the heck? It doesn't, whatever. And yeah, so you'll learn this in class, and there's plenty of videos on it online. Okay, so let's go back and talk about the ratio of the right angle triangle stuff. So you have some triangle, and I'm again going to say that this hypotenuse, this this part of the triangle that's opposite of the right angle. We call that the hypotenuse. I'm going to just say that that's length 1 for right now. And we have some, let's just call it an x value and a y value. And it's sort of definition, we say that the cosine, and actually let's call this r for right now. That the cosine of this angle, let's say theta, equals the adjacent over the hypotenuse, so x over r. But see, like, I think this picture is a little easier to start from here and work backwards. And in this picture, our r is 1, length 1. So let's see, can I just erase this more? Why is it not doing what I want? Erasing for me is very slow. I need to figure out a faster way. Sorry about that. And, oh, there we go. So this is 1 now, and then in that case, will the adjacent over the hypotenuse is x over 1, which is just x. So it kind of goes back to what we were saying here. But more generally speaking, we can choose not necessarily 1, it can be anything. It can be r or whatever. And the idea is that if you scale up this triangle, we can make bigger triangles. We could draw it out this way, like this. There's a bigger triangle. Or you could imagine it going out this way, or some combination of the two, as you wish. But see, these are similar triangles, the bigger orange one and the smaller white one. And so the angles are the same, and the proportions, like all the ratios between the sides should be the same. That kind of goes back to sort of more basic geometry. But think about it. If you've not been exposed to that idea before, maybe Control R, is that redo? No, that's not it. I'd love to know how to Control Y. Oh yeah, it's Control Y. Anyway, okay. So yeah, if you expand, so another way of thinking about it is like, imagine you're zooming in. It's a map, and you're zooming in or you're zooming out. That will change the apparent size of the triangle to you, right? But it doesn't change any of the fundamental characteristics of the triangle, you zooming in or zooming out, right? The triangle remains the same. So that means that the angles remain the same and the ratios between the sides remain the same. So that's true for similar triangles in general. And with similar triangles, yeah, you can think of it as this zooming in or zooming out effect, or this overall scaling of the triangle. It should not affect ratios. So that's why we particularly look at the ratios of these sides. Now it is useful to also just remember to memorize this whole picture, which a lot of you probably already have in math class and stuff. And so the opposite over the adjacent is sine, and then there's also stuff like tangent, and that will be the opposite over the adjacent. And so the way actually I just memorized this, but other people were doing this way of memorizing it called Sakatoa. I think different classes have different adjacent, hypotenuse, different ways of doing it. But if you remember this Sakatoa, it's sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Adjacent just means next to, yeah? And tangent is opposite over adjacent. And that will give you these ratios. And I'll do more videos in the future. There's other geometric pictures that are interesting. For example, tangent. on this. I don't want to draw it here because I think it might be overwhelming, but I'll just draw it anyway. Like, for example, with this line here, if this is our angle here, alpha, like we're doing, we can draw this tangent line, which on both sides, it's not apparent. I didn't draw it that well, but there's a right angle here on both sides. This tangent line here. And I'll just draw one of the things, but maybe I could just draw it better next time. But anyway, you can draw this tangent, and then you want to look at certain lengths, like this length here. This will actually be the tangent, and then there's this other length, this bigger one, that's the secant. And over here we have the cotangent, and over here is the cosecant. Okay, so that stuff is interesting also in its own right, but that's enough of this, I think, generally for today. But there's, let's focus on sine and cosine and how to use them in programming as well. So cosine, again, I'll just draw this. Let's switch to blue. Kind of draw this picture again a bit. Again, we start the angle here. Now you can rethink everything. If you want to start the angle here, your math teacher might get upset with you, but I see no reason not to. And there's certain cases where I personally have, just because I found it visually more satisfying. You could draw the angle here, for instance, and then, but now your cosine has to be over here. Now we've switched them. Well, you could just label this X if you wanted to. You know, you can change everything around. And actually, I think this is kind of a good exercise for you to occasionally do this, because I want you to think generally. Like, you could have two vectors anywhere. So let's say in 3D, you have two random vectors. Imagine that one of these is kind of coming out of the page a little bit. But no matter where these vectors are pointing in the 3 dimensions, you can imagine this flat plane. There's this flat sheet where we can connect them into one on a 2D space. So even though these are arbitrary random 3D vectors that we've chosen, we can draw this 2-dimensional picture connecting them. And so we'll get into it more later, but for example, there's things you want to do, like project one vector onto the other, for example, and we're going to use cosine, and it's very similar to this thing. This is, like I said, I think the projection is more fundamental, more general of a concept. It's really the projection I want you to focus on, and just think that, okay, we've labeled these projections. One of them is cosine and one of them is sine. And the other thing is that here in this picture, we have that the radius is 1. And the radius, if we change the radius, it's very simple. It just becomes, that we draw some arbitrary line. I wish I could draw straighter. Okay, and we just label this R now, and then these projections now change just to being R times cosine of the angle. And sine, this Y value will be sine. R times the thing. And so all we've done, it's similar to what I said before, where we scaled everything by R, didn't we? It's like, again, if you have some picture and you zoom out, that would make it smaller. R can be less than 1 here too. Or if you zoom in, you've made the picture bigger. That changes nothing fundamental about the picture. So what that means is we have to multiply everything in the picture by R. Not the angles. The angles are preserved when you zoom in and out. It doesn't change angles. You might think it does because there's perspective stuff going on. Right, you have like a horizon and stuff like that. But if you think, but that's a distraction. The whole perspective and the horizon and all that. That's a distraction. We're thinking about this, that angles don't change. things scale. And we just, it's the same picture as before. We just multiplied r times everything. R in the hypotenuse as the radius. We call it r because it's the radius of the circle. R is, times this part, the y value. So I'll write this. You can write this vector as with an x component and a y component. It'll just be r cosine theta, r sine theta. And this, by the way, it always wants to do that. Connect those for me. Okay. Those are the x and the y coordinates here. Now we'll also note, since we're doing all of this anyway, there's an equation of a circle. It's related to the distance formula. So what would the distance formula be for r? Like let's say we had these coordinates. We had two numbers. Like let's say, would be a good example. Oh gosh. Well, you could have like 1 over root 2, 1 over root 2. Could be any numbers. Well, not any numbers. They have to be on a circle. You can have root 3 over 2. If you want to play around with examples. And 1/2. That's also going to be on a circle. We could, let's see, do root 3 and 1 will be on a circle. So let's say I give you this and you want to write this picture. Well, I've given you r cosine and r sine. How do you calculate r? Well, it's a distance formula. So the distance formula and the formula for the circle, the equation of a circle, are basically the same thing. So r squared equals x squared plus y squared. Usually it's written the other way. X squared plus y squared equals r squared. That's the equation of a circle. And distance usually is written like, I'll show you how it's usually written, but it's really the same thing. If I square both sides, I get distance squared equals, no square root now, right? Now that I've squared it, you see that this is the same formula as the formula for the circle. And that makes sense because the circle is fixing the distance from a point. We're fixing distance. So if you think about it, it makes sense. That's what this is measuring. It's measuring the distance, giving an x and a y value. Now there's a difference here that we usually say that distance can only be positive. Okay. And if you were going to challenge that idea and say, well, why can't distance be negative? I mean, we have negative numbers, which are useful. Like we talk about negative temperatures. We talk about owing things. Like I could have apples and bananas, but I might owe someone apples and bananas. I might owe someone money. Negative numbers are useful there. Also elevation, right? We choose an elevation that's 0. Then we have, after that, we have negative elevation. Same thing works with voltage. You actually have to compare voltages. It's similar to elevation. And so negative numbers are useful there. What is special about an area or a distance where we suddenly say, oh no, it's impossible there? Like, oh, a lot of people, when they first learn about negative numbers, they find it disturbing and challenging and annoying. And we're kind of, if we only accept positive distances, we've kind of done the same thing again, where we're saying, no, there's no such thing as negatives. And so that's where you get into the square root of -1 and imaginary numbers and complex numbers and all of that stuff, in my view. That's the way I think of it. We expand our horizons to think about negative distances. That's how I think of it. So, okay, but we're not going to go there today, but I'm just going to say as a side note here. But normally people are sort of stubbornly saying that distance is always positive, but then they'll go and they'll teach complex numbers, imaginary numbers, but they'll still insist that distances are positive. Well, whatever. I view it as talking about negative distances, negative areas, right? Okay, which I don't have a problem with. If you have, again, similar to all the other examples, if you have positive 25 meters squared, why can't you have negative 25 meters squared? It's okay. And that expands our horizons out into the world of complex numbers, which gives us a lot of rich tools that are very powerful and useful in mathematics. Kind of essential, really, in math and physics are those complex numbers. Okay. So this is a circle and distance, and so let's use this example here, this third example. If we plug in the numbers, we get r squared equals square root of 3 squared is going to be 3 plus 1 squared is that. We get r squared equals 4. Wow. And r equals plus or minus 2. Some people are just going to say, I'll write the plus or minus 2, even though probably at this point most teachers go, well, our distances can only be positive, so we just do 2. But what happens if you choose a negative distance for your radius? It just points the other way. And then it's the same thing, basically. It doesn't really matter, does it? So 2, anyway. So we've calculated a radius, and that's the same thing as calculating a distance. If I'd given you these, but it's distance from the origin, right? If you want the more general distance formula, we need x minus some point. I'll just call it x naught squared plus y minus the coordinate of some point squared. So the x coordinate of some point, the y coordinate of some point. So if this is our, so you know, another way to write this, we can just write this as, let's write this as like x2 minus x1. So we have 2 points. y2 minus y1 squared. So this is the same thing. Basically, we've just shifted things by this other point. Because in general, if you have some crazy equation with lots of x's over here and lots of x's over here, or sorry, y's over here or whatever, and if you just want to shift it, say shift it to the right by 2 units, you find your x's and you just say you want to shift it right by 2 units, do x minus 2. So it's kind of like you do the opposite here. You want it to go to the right 2, you do minus 2. So the idea is that when x is 5, now it's going to output 3 here. I don't know. Just remember that. You can work out some examples if you want. But that's the idea. We're taking a point and doing the same kind of thing here. That's why at first I was just writing x minus x naught. I was thinking that we have this point x naught somewhere. There's x naught, y naught, and out here somewhere we have some other point in general, some x and y. That's why I was writing it the way I was writing it, x minus x naught. We've just shifted from the origin over to this point here. That's all. And also, same thing for the y. I didn't say it, but same thing for the y. If you want to shift up by 5 units, you find your y's and just change your y's to parentheses y minus 5. Okay? This will shift everything upwards by 5 units. Because the point... Yeah, anyway. So Okay. Back to cosine and sine. So this is just a more general picture. And I'm also saying you should practice, even like when your math teacher is not looking, practice starting with the angle up here. Why not? Because I want you to think more generally. Okay, back here, in this case, so when we'll probably study projection. Now, so what I've done here is we've taken a 3D vector, two 3D vectors, and no matter where they are in space, you can draw this two-dimensional picture. Do you see that? Try in your mind. Start with one vector, and then just point your finger in some direction in space, and then start choosing other ones, and see that you can always have this flat sheet connecting both of those two vectors. So there's always this two-dimensional picture that goes there. And normally, so let's choose the smaller of them to start with, and we'll just label that R. Well, again, you could label it 1. So let's say if this were the number 1, then this projection down here, if this is our angle theta, this projection down here will be cosine of theta. Now what we've done here is we've gotten the formula for projection kind of for free, because instead of defining cosine and sine with these triangle ratios, I've focused on the whole projection side of things. If you really focus on that aspect of the definition, then it's obvious here that this picture is the same thing. And then if I change this from 1 to R, well, I just multiply this times R. It's a scaling of the picture. Remember that R can be less than 1 or more than 1. It doesn't matter. And so this is how you do a projection. Now, it's a little like normally you might have you'd have two different sets of coordinates, not just an R value, but you can compute the R value and then do the projection. We'll talk more about projections in the future, but I wanted to equip you with the thought process to where you can work it out yourself. And I also want you to not be married only to this unit circle picture. I want you to think of angles where you position them in different places in space. That's why I brought up this 3D example. But this is even more powerful because it doesn't matter how many. It could be 3 dimensions. It could be 4 dimensions, 5. It doesn't matter. It doesn't matter how many dimensions you're talking about. There's always this 2-dimensional picture between vectors in n dimensions. Our n-dimensional vectors in our n-dimensional vector space will always boil down to this. You can always take this 2-dimensional slice between them. So this is extremely powerful. It's part of what makes the story of vectors so powerful to begin with, is that we can take these slices of an n-dimensional space. And that's part of why there's this obsession with sine and cosine. If you walk into a physics classroom, there's a fair chance that there's a bunch of sines and cosines written all over the board. It's not only talking about 2 dimensions. It doesn't matter how many dimensions we're talking about. We can relate 2 vectors through this 2-dimensional picture and using sine and cosine. So it's very, 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 very powerful. Okay, so I wanted to kind of expand your mind on that and encourage you to think about other examples. I mean, there's a famous situation of a pendulum. Okay, this pendulum is part of a circle. If you spun the pendulum at full speed, it would trace out a circle going around and around. So it's part of a circle, and now your angle is up here. So, yeah. Here's an example where you can't only think of this. You just need to reorient this unit circle for yourself somewhere else. That's all. And I suggest being comfortable with that. All right, and last thing I want to talk about today is the cosine and sine functions themselves, how they're useful in programming a bit, maybe what the functions look like. So actually, I'm not even going to draw the coordinate plane. We just pick two arbitrary vectors. Now, we want to talk about cosine and sine, and what the differences are. Cosine is kind of my first go-to because, so let's say this is our first vector, and now we choose a second vector. It can be anywhere. We want the starting point to be the same. I talked about this in the long video about what is a vector. We want the starting place, the tail of the other vector to be the same, but we can choose any other point. So here's a point, that will be the head of our vector, okay? But before choosing some point over here, let's choose points and there's a one-to-one correspondence now between points and vectors because I've specified the tail. So any point I choose, there will be a vector coming out to that point. So let's now choose points that are very close to the head of this first vector. So very close. So let's say like right here. So it's very, very close. So I can tell you that the cosine of this angle here is very close to 1. And if our angle were 0, if there's no angle, the cosine is 1. And that's just sort of useful because when something is the number 1, I think of this as an identity, the identity. So the number 1 is a number that you multiply times something and you get back the original thing. It doesn't change the thing that you multiply it with. So this is kind of useful because the cosine of this angle between them, let's just call it theta, when there's no change in the vector, there's no angle change or anything, the cosine of the angle will be the number 1, which is it's useful. It's something that we want. We want this identity that we can multiply things by, and it leaves things unchanged. Because if we're talking about the vector being unchanged, we want, let's say we have initial conditions in our system, some kind of starting configuration, and we're at time equals 0. No matter what crazy things we decide to happen later, at time equals 0, I want there to have been no change whatsoever. And so this cosine theta is extremely useful in all kinds of different applications and circumstances, because at time equals 0, when there was no change in this vector, that means that we could be changing things in all kinds of different ways, but at least if we take the cosine of this angle, the angle is 0 because there's no change, and it gives us 1, and we can now multiply this cosine theta times other things. It's kind of a starting point for thinking about what kind of equations we could make that are going to be useful for our circumstances. This is kind of my go-to, because at t equals 0 with no change, the cosine theta is 1. So it's extremely useful for that reason. So I know that's kind of maybe confusing and sort of hand-wavy for a lot of people, but I'm just emphasizing this usefulness of cosine. Okay, and so now let's talk about programming a bit. So, and I'll very quickly just graph these functions. I don't want to work out all the logic of it. There's plenty of videos out there. But if here we have theta, and then we have the output values, so I'll just write cosine of theta here. Then when theta was 0, cosine theta is 1. And I'll just draw some things. And it goes like this. Here it'll be -1. Now, what are the x values? We use radians. Radians might seem mysterious and confusing to people, but I'll explain radians. That what I want you to do is, again, go back to the unit circle. Okay. And think, if this is all you have, let's say you're an ancient Greek person or something, and you have this length of string that you've decided that's unit 1, that's length 1. What would you do to come up with a system of angles, for measuring angles? You want to communicate with your fellow mathematicians and philosophers or whatever back then, and you want to have a way of measuring angles. What would you do? I want you to really, it doesn't have to be today, right now, but I want you to really think about this at some point. What would you do? There's really two possible things that I can think of. One is that you would measure angles based on the length that's carved out by this. So if your angle is way over here, you focus on this length that's traced out by the angle. And the other option would just be to focus on the area that is being traced out, I guess, by the angle area. It turns out I actually like area a little more than the length. And the reason has to do with hyperbolic trigonometry, which is totally different, because in hyperbolic trigonometry, we can't use these lengths. We have to really focus on the area. So it's more general for me. However, that's not the system that we've kind of all agreed on. We focus more on the length, but both of these are valid ways of measuring the amount of angle that's being traced out. I can't really think of any other way. Can you, if you can think of one that would make sense, leave it in the comments. But either looking at this length that's being traced out or the area that's being traced out. Okay. And so, well, let's look at the length first. And, well, we have this length, for example, all the way around here, which they've measured, and they compared, okay, what is the ratio between this radius of 1 and this half circle here? And they measure it out to increasing accuracy, and it's just some special number, which we, of course, call pi. And so if pi and radians and all this stuff seem very mysterious and confusing and you get lost, I suggest going, like, putting an afternoon aside and thinking, if you were one of the ancient Greeks, what would you do? What would you do what would you create as a system starting from scratch? What could you possibly do? And it becomes fairly obvious that, like, this ratio here is really important. You could also have just chosen this one. And some people say that this is better, and they label it tau, Greek letter tau, and it's whatever, 6.28, whatever it is. And there's actually a movement to use tau instead of pi. Okay, but if we're using pi, then this full length around the circle is 2 pi. It's twice what we were talking about before with half the circle, right? And so, if you think of it this way, you'll never have trouble remembering that the diameter, I'll put d diameter, equals 2 pi. This is just a general, I guess I could write d. I just was using that as distance earlier, so. Yeah, diameter is 2 pi, right? That's clear here. And the way that we've decided to talk about angles at all is as fractions of pi. essentially. So one way around the entire circle is 2 pi. Halfway around the circle is pi. And if we go, I'll leave this up here. If we go, I'll use a different color. If we go to here, it's half of, this was pi, so this is pi over 2, and so on. The 45-degree angle is going to be half of that, which is pi over 4. Oh my goodness. Pi over 4, and so on. So fractions of pi, that's radians. It's based on this arc length, okay? The length that is traced out by this angle. That's where this concept of a radian measure comes from. It's a very obvious way to measure angles, to talk about angles. Degrees, on the other hand, is very arbitrary, right? Okay. So going back here, when I'll just write this out, this is pi. Let's look at that one first. When the angle is pi, cosine is going to be -1. So why does that make sense? Well, we have this original picture, and remember that our cosine is the shadow left by this projection, the shadow along the x-axis. So when we go from here, what color should I use? Orange? No, I used orange. Red. When we go from here all the way to here, then the shadow started at 1, right? When the angle is 0, this length is 1. And then when it was up here, the shadow became 0 at this moment, at, what is that? Pi over 2, right? Then the cosine was 0. Then when we choose to label these with negative numbers also. So instead of saying that this over here, the shadow is 1, we give it this negative distance, something that was controversial a little bit earlier, but we have no problem. Math teachers don't blink, they don't bat an eye when we use negative distance here for some reason. So here we say it's we call this a negative distance that is being projected out now. Okay, so cosine over here will be -1. Here again, it will be 0. And then it goes back to being +1 over here. And the other things that are kind of useful to remember are just that, let's go green, that when we're at this 45-degree angle, what is that in radians? Yeah, it's pi over 4. Here, the numbers that come out on the unit circle are 1 over root 2 and 1 over root 2. Of course, sine and cosine needs to be the same here because there's kind of symmetry in this drawing. And this length over here needs to be the same as this length over here because it's symmetrical. If you turn your head by 45 degrees, the whole picture is symmetrical, so these lengths have to be the same. So they come out to 1 over root 2, 1 over root 2. We can see that by looking at the distance function, because distance, so we have, let's say we didn't know that number, so I'll call it n. Let's call it u for no particular reason, because I like ultraviolet. So u. Some number, and we're saying because it's symmetrical, it's again the same number. And this has to equal 1 though. So 1 equals that. We square both sides, and we get 1 again equals u squared plus u squared. And we simplify, oh my goodness, 2u squared. And so 1/2. And so u equals plus or minus 1 over root 2. Now, I don't know why. Math teachers hate when you have radicals in the denominator. I think this is something to do with tradition. I really don't care. I like it like this. I have no problem with that whatsoever, but they often want you to multiply top and bottom by 1 over root 2, or sorry, by root 2, and we get root 2 over 2. So they'll normally write it like that. I really don't care about radicals in the denominator. I've never cared about it. So that's my personal preference, actually, is like this. So that's useful to remember. There's also this other one, which is useful to remember, which is at the angle pi over 3. When the angle is, it'll get a little messy, but when this is pi over 3, it's good to remember that this will be root 3 over 2, 1/2. And if you get confused, because over here it's going to be the opposite, it's going to be 1/2. Do I have this? I think I maybe have these backwards. I was just about to say, if you get confused on which one is which, yeah, it's got to be the other way. Yeah. And I'll explain how I remember that. It's going to be 1/2 root 3 over 2. Now it's simple. But here, it's, again, there's symmetry here. If we go, this is pi over 6. It has to be where the x and y values are flipped because of symmetry. And if you look at these, which one's bigger between 1/2 and root 3 over 2? Well, the square root of 3 is bigger than 1, right? And so here, the denominators are the same, but the numerator is 1 here and something bigger than 1 over here. So root 3 over 2 is clearly bigger than 1/2. And these x values and y values, I mean, you can just look at them for what they are, x values and y values, or equivalently, you can look at them as these projections, these shadows, onto the x and y axes. And clearly the x value here is bigger, right? This distance along the x-axis is clearly larger than this distance along the y-axis, which means that our x value should be bigger. So that's how you remember which is which. And so this is going to be for pi over 3, and pi over 6 is the smaller one. Or sorry, this is it pi over 3? Yeah, it's pi over 3. And if this is totally new to you, I suggest watching a few more videos on practicing and getting familiar with this. I think this is just really important for understanding kind of this is basic geometry, but it's not so much when we have these coordinate planes. The ancient Greeks, they did not use coordinate axes. This was really popularized by Descartes, which is why we call it the Cartesian plane, named after Descartes. I don't know why we don't call it the Descartesian plane or something. I guess in French, if you say Descartesian, it sounds like of Cartesian, so that's why it's Cartesian. Maybe it's even like a mistake or something, but anyway, Descartes? I wrote that wrong. Descartes. Not that. Descartes. So, yeah. He didn't necessarily invent this idea. He was the I think, therefore I am guy. Philosopher and mathematician. Very important. I think, was it the I think it was earlier than the 1700s. Maybe 1600s. 1600s or 1700s. And he didn't necessarily invent this whole idea of having x-axes and an x-axis and a y-axis, but he definitely popularized the idea and made it very famous. And it's useful in all kinds of, I don't know if you call it analytical geometry, but if you have some complicated problem with circles and triangles and everything, sometimes putting it on an x and y axis can make things easier to compute. In the old days, thousands of years ago, they didn't have that idea. And a lot of the math problems that your teachers will give you have to do with these angles of 45 degrees, 30 degrees, and 60 degrees. In other words, pi over 4, pi over 3, pi over 6. But you also need, it's good to be able to write out this entire unit circle, which it has these angles, including along the, at the coordinates 1, 0, 1, 0, 0, 1, negative 1, 0, and 0, negative 1. But also all of these. It's the same exact coordinates. You just change the plus and minus signs in front. So over on this side, the x values get a negative sign. If it's over in this quadrant, both x values and y values have negative signs in front of them. And over here in the fourth quadrant, the x values will be positive and the y values will be negative, right? Okay. So, but it's good to practice writing this out, the unit circle, and memorizing it. It will equip you for more difficult problems in geometry. Okay, so at pi we had negative 1. At pi over 2, we have cosine is 0, right? It goes through the axis. And it just, it's periodic, so it just continues like this forever. So this is up till here. This is one period, we say. I'm going to get rid of this because it looks like it's part of the graph. When we say it's one period, we just mean that the graph is repeating, and one period refers to like one iteration of the graph. Okay. So after that, it just keeps repeating and forever. But this will be now at 2 pi. So at 2 pi, we've done 360 degrees. We've gone all the way around, and we're starting again. So that makes sense, right? And same in the opposite direction here. And it keeps on going. Here's at x equals, or theta equals, negative 2 pi here. So I should maybe write this along the x-axis to be clear. Negative 2 pi. Negative pi, etc. Where it crosses the x-axis, I didn't draw it very well, but that should be negative pi over 2. So you see that cosine theta has this symmetry along this y-axis here that we've labeled cosine theta, which simply means that this projection, whether you go up this way, which is, we're calling this positive, if we're talking about theta or alpha, our positive angles go that way and our negative angles go this way. And that's just an arbitrary choice. And it doesn't matter which way you go for cosine. The projections, those shadows along the x-axis will come out the same, whether it's positive or negative. But for the y values, we've made this kind of arbitrary choice where we've said that this direction, we've said this is positive along the y-axis, and down here is negative along the y-axis. And that's a choice. We can flip everything upside down and label things with the y-axis down here if we wanted to, right? So which direction is positive and which is negative is up to you. I'd like to think, one man's positive axis is another man's negative axis, and kind of tried to think a little bit openly about that. And going back to here, So our graph of sine, I'll just do here, goes through here. It's the same graph, it's just shifted. And it goes through the origin. So let's label this sine of theta and theta. So when theta is 0, sine is 0. Again, think back to those shadows or projections and work out the logic. You might want to go through this whole thing and check each position on here. You don't need to do pi over 3 and pi over 6, but all of the sort of 45-degree angles, check them mentally in your head. So be able to recall the unit circle and these numbers from memory, and also be able to graph cosine and sine of theta. And if the information I've given you here today is not enough, there are plenty of videos out there. The reason I'm making one of my own videos here is that I have some unique perspectives to offer, not totally unique necessarily, but some difference in teaching from what you normally get, I think. For example, starting from the projections rather than looking at these ratios as being the fundamental things. It doesn't really matter. You can just choose how to think about it. But that's how I think about it. I value the projections and shadows as being more fundamental. Okay, now from a programming standpoint, these are useful, of course, for all the geometric reasons, and they come up all the time in physics and all kinds of applications. When you're projecting one vector onto another, you use them. When you're calculating normals, like when you're doing lighting, so if we have a surface, we have the normals are these things that stick up they're perpendicular to tangents. So your tangent line, for example, would, on this point, it would go straight through. Like, when you're infinitesimally close to the point, it is parallel to the point. So this long line's going forever, so it's this tangent line, okay? And the normals are perpendicular to the tangent lines. So, and you could also point these normals in the opposite direction, and those might be inverted normals. Like if you have some cube, you want the normals pointing outwards in the cube, not inwards. Okay, this is just graphics programming stuff. And normals should generally be normalized, meaning they are of unit length. Normal vectors are of unit length. Okay, so yeah. Normalizing vectors, that's a common function that you see all the time. And so, yeah, if you have light coming in, we use the dot product, which is similar to projection, and it'll use cosine. And so there's all kinds of applications for this stuff that are obvious. But I want to talk about slightly less obvious ones that I use all the time, which is simply when I want to test something. So I'll be looking at someone's code or something, and there's some complicated function, I don't know what it does, and I want to test it. So we have some function, and we have some output to this function. And maybe I don't even know what kind of output, let's say, I can see that it's a number, I can see what type is being output, but I don't know anything about the structure of this at all. So what I'll do is I'll map this to some color value and graph it somehow. So, commonly. Or it could be I just output it to a terminal. You could output it to a terminal, or you could output it to an RGB value, for instance. This is how color is normally done. And I'll just choose one. Choose red, for example. And then 0 and 0 is fine. Doesn't really matter. Choose whatever you want. And this will map it into the red values. Now, yeah, so that's a whole other topic, but in graphics in general, color is just represented with a red value, a green value, and a blue value. This has to do with how our eyes process color, so it's beyond the scope of this video. Okay, so RGB. So now what I'm used to is normally that these range from 0 to 1 each. Okay, that's one way of doing it. Sometimes you'll see where it ranges from 0 to 255. This is because this is for each of them. So this is because this is 1 byte of information, which is 8 bits. I don't have time to explain why we have this, why we often do things this way historically, but this is something you'll see. And the number is, it's because 2 to the 8th power is 256, and because we're including 0, we have from 0 to 255, that's a total of 256 values. So 1 byte can store a value from 0 to 255. So color was often being stored with 3 bytes. But anyway, we might have this 0 to 1.0 value. So let's say I have this function and I don't know what kind of numbers come out of it at all. What I'll do, typically let's start with cosine and just pop this function into cosine. And we could vary it with t. So if there's an x, I'll swap out all the x values with a t for time. And then we'll get all kind of a huge range of different things. So I might swap, I just look through the function, this complicated line of code, switch all the x values or whatever values, h, whatever it is that the input is, switch all of those to t, set up some kind of clock system or something. So time is being used as an input, potentially. It doesn't matter. I might do that, I might not, depending on what I want. But now that I've done this, I know that the output is restricted but from -1 to 1, and that's extremely useful. Now I've restricted this output. Now I'd actually like to get it to be from 0 to 1 for this color example. Sometimes I'll leave it as is, pop that in, but I know I'm only getting half of the information, right? Potentially. So what you need to do is, if you want this to vary from 0 to 1 instead, what I'm going to do, first I multiply this by 2, put a 2 here, now it'll go from -2 to 2. This is like that previous talk about scaling stuff. You just multiply something by a number and everything scales. And actually I did this wrong. I should do 1/2. Yeah, I want to make the range smaller. The output, I want it to be smaller, so 1/2. Actually, I usually start by thinking, sorry. The first thing I do is I add 1. Add 1 to get rid of the negatives. Okay, so first we're going to add 1. Now the range is from 0 to 2, right? Then I take all of this and divide by 2. Now we'll go from 0 to 1. Okay, so cosine of this crazy thing. So you might have this crazy thing. So let's say h is equal to, so depending on the language, you know, it'll have like, we don't care, just h, whatever. I picked a letter, is equal to this thing, this crazy thing. I don't know what the output is. And then I just let's do s or whatever equals cosine h plus 1 divided by 2. Then I'll do color equals some kind of vec3, and I'll plug in S. This is just pseudocode. It's not any specific language. But yeah, these are just zeros, okay? And then I'll output this anywhere, somewhere. And then I'll get this color representation of the function. And then I just need to think about my input. Am I varying my input enough? Again, I could use time. Then here for my time variable, if I think it's going too slow, just start multiplying it to make it 30 times time. Or if it's going way too fast, divide time by some number. Start with 2 and then keep doubling your factor. Make it 4, then 8, 16, 32. Eventually, you will find a way to make sense probably of what's going on. Or at least you'll have some visual demonstration of what's happening. So I mean, that's sufficient. But sometimes sine is a little better if you want... I can't remember the explanation on why off the top of my head. It doesn't... Either of them are good. With this map, it's sometimes hard to see exactly where your input was 0. It's like, let's say you're outputting somewhere on a screen. And it's kind of like finding exactly where it was 0, where the midpoint of the screen is. It can be hard sometimes. You might be able to fix that by using sine instead, but probably cosine is good enough. So anyway, so I use cosine and sine a lot. I find myself doing this from time to time. So I thought I'd share. This is one use, which is I don't see people talking about much, but I think experienced programmers probably do it a lot. Okay, so that's enough for now. There'll be more to talk about in terms of uses of cosine and sine. For example, projections. And when we sort of talk about that in a more elegant and complete way, we'll use the dot product, which is one of the operations that we commonly do with vectors. And I don't know, at some point we might talk about the cross product as well. And not related to programming, but related to physics and math are these other things called hyperbolic trigonometry. Instead of taking place on a circle, it takes place on a hyperbola. Oh my god, what did it do? Oh, that's okay, actually. Hyperbola is this shape, this kind of thing. We can actually do trigonometry on this thing. And this is related to special relativity. So you may have learned, we can actually, physicists have actually figured out that you can create a time machine going into the future. Not necessarily the past, but definitely into the future, because time and space are relative, right? So the simpler version of that is special relativity. And on the one hand, the math can be viewed as simple because it's actually, the foundation of it is really based on the Pythagorean theorem, and it's very much the same thing that we've been talking about today. So you can set up special relativity just using middle school level math, actually. But there are more sort of elegant packages and ways of thinking about it. For example, this hyperbolic picture and using matrices. Not to mention if you get into connecting it with electromagnetism, then it really gets more complicated. But yeah, special relativity is interesting for many reasons, but one is that you can explain it using middle school math, actually. But then you can also make these more complicated, elegant, sort of, I think of them as packages, mathematical packages, elegant ways of expressing things. So if I ever talk about special relativity, we'll definitely talk about the hyperbolic trig, which is cosh and sinh. But usually in high school you don't even study these. But I think they're super, super interesting, and they're kind of hidden throughout geometry. So if you're interested in math in general, actually this is super interesting. There's so much to say about hyperbolic trig. So I may be talking about that. It's interesting in its own right. And then it's also kind of the foundation or fundamental stuff in special relativity, at least from one way of thinking about it. But that doesn't, you don't need that for programming. Actually, there could be, using cosh or sinh could actually have similar, maybe even better uses, similar, like in the same spirit as what I was showing here. I have to think about that. It kind of depends. I think they're better at dealing with when things go off to infinity and sort of trying to collapse that down a bit. But yeah, because when if you have some function that flies off to infinity, well, you will see it here because your cosine will start going whoa like crazy. It'll have a very high frequency. So, and that's another thing, another topic is that when you start getting into frequency and angular momentum, so we might talk about a particle moving in a circle and it's speeding up or slowing down, it's accelerating, etc. And we talk about these waves, and we talk about frequency and angular velocity, angular acceleration, and torque. So torque is like force, but talking about angular momentum. Or I guess maybe it's acceleration is the better analog. I have to check. I can't remember off the top of my head. So yeah, lots of other things to talk about. Oh, color as well. Yeah. But anyway, that's it for today. Thank you.